Hi everyone, welcome to this full walkthrough of BMO Round 1 from 1997. In this video I'm going to go through all 5 problems carefully and explain the main ideas behind every single solution, basically just trying to make the reasoning feel natural as opposed to just presenting a finished proof as I sometimes do on my TikTok page. Some of the questions as you're going to go on to see are quite algebraic, whilst some are more combinatorial, and there is one geometry question which is going to be quite nice to go through. Okay. So as you can see, these are the first 3 problems from that year. And the first is to do with basically reversing a 4-digit integer and achieving 4 times the initial number you basically started off with plus 3 once you reverse it. So we have a digit reversal problem for number 1. For number 2, we have this sort of recurrence relation here, which we'll explore in more detail when we go through that. And the third is a coin counting problem, which is basically tied into combinatorics. Okay, cool. And then these are the last 2 problems. So this is from 1997, so there was only 5 BMO1 problems. I think there's nowadays there's 6. But yeah, as you can see, these are problems 4 and 5. Problem 4 is going to be the geometry problem that we're going to look at a bit later. Basically talking about a midpoint quadrilateral inside a convex quadrilateral. And a convex quadrilateral is just basically a quadrilateral whose angles are each less than 180 degrees. So you can just think about it like that for the sake of the problem anyway. And then problem 5, we have an inequalities question split into 2 different parts. Yeah, okay. And so that's basically going to be that for the problems here. I'm going to skip this slide. That's not really useful. And without any further ado, let's get straight into problem 1. So we're told that capital N is a 4-digit integer with digits A, B, C, and D, and that reversing its digits gives a new number R of n. As you can see down here, we call that new number R of n, just the reverse of basically our 4-digit number. And we have this condition that the reverse of our 4-digit number is 4 times our 4-digit number plus 3. Okay, so the first sort of obvious thing to do, or hopefully it seems fairly obvious to do anyway, is effectively just to translate the digit information into an algebraic expression or equation which we can work with. Okay, so obviously, therefore, you can write capital N, right, since it's a 4-digit integer with digits A, B, C, and D. We can write capital N as 1000A plus 100B plus 10C plus D. And of course, reversing that integer is going to give us R of n, which is going to be effectively 1000D plus 100C plus 10B plus A. Okay, so what we're really trying to solve here is basically this equation, right? So we have 1000D plus 100C plus 10B plus A, and this thing on the left-hand side here, that's our R of n. And then on the right-hand side, we have 4 times capital N, because remember, capital N is just 1000A plus 100B plus 10C plus D, plus 3. Okay, so that's just translating this equation here into an algebraic equation, which we're going to have to basically solve. We're going to have to find the possible values for A, B, C, and D that actually make this equation true. But we're going to have to sort of look at the digits one by one. Okay, so yeah, ultimately what we're trying to do here is just force the digits of our number to be specific things and see what we get with that. Okay, so yeah, cool. Next slide. Okay, so first things first, we know that R of n is a 4-digit number, okay, because we started off with a 4-digit number, so reversing it is going to keep that a 4-digit number, right? Not going to change that fact. So since R of n is a 4-digit number, the right-hand side, 4 times capital N plus 3, is also a 4-digit number, because in this case, we're supposing that R of n equals 4n plus 3. So therefore, 4n plus 3 has to be less than or equal to 9,989. And that directly, obviously, when you sort of solve for n in that case, you get that n is less than or equal to 2,499. Okay, so that immediately tells us that actually our thousands digit, which we labeled as capital A in the previous slide, so this sort of digit here, which corresponds to our sort of thing being multiplied by 1,000, has to be either 1 or 2, right? Because this is our base 10 expression for capital N, and we know that capital N has to be less than or equal to 2,499, so the first digit has to be a 1 or a 2. Okay, and we're not really going to be using the standard, well, we're not going to be using the sort of idea that you can have 0 at the front. Okay, we're going to say that that's not, that doesn't happen, right? So when we talk about a 4-digit integer, we're talking about something greater than or equal to 1,000. That's the sort of thing that I'm supposing. I mean, I don't think it changes anything anyway, but just worth mentioning here. So that's why I've said that A has to be 1 or 2 as opposed to being 0. Okay, so yes, we know that the thousandth digit of A has to be 1 or 2. And now we need to use a bit of some interesting modular arithmetic stuff here. So if we compare, well, if 2 integers are equal to each other, right, as they are up here, right, if we have that R of n equals 4 times capital N plus 3, then we know that the remainder when they're divided by 10 has to be the same, right? Because they're literally the same thing. R of n is equal to 4 times capital N plus 3. So when I divide both of those things by 10, I'm going to get the same remainder because they're literally the same number. Okay? So effectively doing that, and basically dividing both sides of this expression by 10, and figuring out what the remainder is going to be. Well, if we divide the sort of left-hand side expression by 10, 1000d is a multiple of 10, right? 100c is a multiple of 10, and 10b is a multiple of 10. The only thing here, which we don't necessarily know is a multiple of 10, is a. In fact, we know that a can't be a multiple of 10. It has to be 1 or 2, right? So when we divide this expression by 10, the remainder that we're going to get is a, because we can factor 10 cleanly out of these first 3 terms with it and then get a by itself out of that, right? So basically, the remainder when I divide my left-hand side here is going to be a. When I divide my right-hand side here by 10, well, again, I'm going to have this 1000a term, already 4000a term here, right? Because we're going to expand the 4 through the brackets. But this first term here is going to still divide by 10 because it's 4000a and 10 divides 4000. This second term, 400b, is also going to be divisible by 10 because 10 divides 400. The next term, 40c, is also going to be divisible by 10 because 10 divides 40. But the thing that we don't know is divisible by 10 is 4d plus 3. Okay? And so basically, we know that whenever I divide this right-hand side by 10, the remainder that I'm going to get is 4d plus 3. Okay. Now, obviously, d is an integer. So, d is a digit, is what I mean to say. So it could be something like 9, in which case 4d plus 3 is going to be, 39. So you might think, hold on, but we're saying the remainder when I divide it by 10 is 39, which is a bit unorthodox, right? Because you would expect the remainder to be between 0 and 9, right? Because the remainder of 39 it just doesn't really sound correct. And you'd be right, but that doesn't really matter because effectively we can say that the remainder is 4d plus 3, but then evaluate that even further once we actually know what d is. Okay, because basically the remainder of 39 is the same as the remainder of 9 when you divide something by 10. Those are the same things. You just have extra like 10s in your 39 and not in your 9, basically. So don't worry too much about the fact that 4d plus 3 could be a two-digit integer. Just know that whenever I divide that right-hand side by 10, I'm going to get a remainder of 4d plus 3. Okay, 4d because I'm basically expanding this 4 throughout the brackets here. So this 4 is going to be multiplied by d, and then the plus 3 is from this. Okay, and obviously 10 divides everything else. So the remainder that I get when I divide this side by 10 is going to be 4d plus 3, which I can evaluate further once I actually know what d is. But the main point here is to say, basically the following thing, that we know that a is going to be congruent to 4d plus 3 modulo 10. What that basically says is that since we know that both of these, since we know that r of n is equal to 4n plus 3, the remainder when I divide both of these numbers by 10 is going to be the same. So basically, a remainder of a, when I divide it by 10, has to be the same as the remainder of 4d plus 3 when I divide my integer by 10. So what this is saying is that basically these two remainders are the same. That's basically what it's saying. So, and the mod 10 is because I'm saying that I'm dividing both sides of my equation by 10, and the remainders that I get when I divide both sides of my equation by 10 are a and 4d plus 3 respectively, so they must be the same thing. Okay? So this is kind of the more formal way to write that, basically saying that a and 4d plus 3 are the same remainder modulo 10. Right? Or leave the same remainder when divided by 10. Okay, now we know that d has to be an integer, right? And it actually has to be something from 1 to 9. Because, why do we know that d has to be something from 1 to 9? Hold on. Because we have a 4-digit integer. Oh, it says with d not equal to 0. I think that was given in the question. Let me go back up. Yeah, okay, so it gives in the question that d is not equal to 0. Okay, fine. So we know that d has to be between 1 and 9. And so as d is some integer between 1 and 9, we can effectively just check the values of 4d plus 3 when you divide that by 10, right? Because that's the right-hand side of this congruence here. So if d was 1, then 4d plus 3 is 7. The remainder when I divide 7 by 10 is just 7. When d is 2, 4d plus 3 is 11. The remainder when I divide that by 10 is going to be 1. And then you keep computing those, and you get this sort of string of remainders here, okay? However, we know that that basically has to be the same as a, because a is 1 or 2, okay? And the point is that since a basically is the same remainder, or leaves the same remainder as 4d plus 3 when divided by 10, and a has to be 1 or 2, and 2 doesn't appear in this list of possible remainders for all values of d from 1 to 9, we know that a has to be 1. Because 4d, if a was 2, then it wouldn't be possible for these two remainders to be the same, or for a to leave the same remainder as 4d plus 3 when divided by 10, because a is going to leave a remainder of 2, but 4d plus 3 is never going to leave a remainder of 2, so this statement wouldn't be true. So the only way that this statement here is going to be true is if a is equal to 1. So a has to equal 1, and we know that for sure. Okay? And the only times when a is equal to 1 are for values of d which were d equals 2 or d equals 7. So we also know that d has to be 1 of 2 or 7. So instead of now 10 possibilities for the outer digits, we basically just reduce to sort of 2, which is quite nice. So at this point, we can substitute a equals 1 into our initial equation that we had sort of up here, that I sort of wrote at the very beginning, our algebraic expression of this equation here. And because we know a equals 1, we're substituting a equals 1 into this expression to get this thing over here. And then basically rearranging that to get this expression here. So 996d plus 60c minus 390b equals 4002. And then we're dividing that by, what are we dividing that by? 996. Yeah, we're dividing that by 6 to basically get this equation over here, right? So we have, just by rearranging this equation up here, we get this equation, right? We're bringing all the terms with d's, b's, and c's onto one side, and the constant on the right-hand side. And then dividing both sides by 6, we get this equation here. So 166d plus 10c minus 65b is 667. And there are two cases that we can now split into. We know that d has to be 2 or 7, so we first of all assume that d is equal to 2. If d is equal to 2, then you get this thing here. We get 332 plus 10c minus 65b is 667, which rearranges to give that 10c minus 65b is 335. Okay? However, at this point in time, if we're assuming that 10c minus 65b is equal to 335, but we know that 10c minus 65b is less than or equal to 10c, which is less than or equal to 90, right, then that's impossible, right? Because we can't have 10c minus 65b being equal to 335, but also being less than or equal to 90, right? Because b is a positive integer, so 10c minus 65b is going to be less than or equal to 10c. And obviously c is a digit, so c has to be at most 9, so this term here has to be less than or equal to 90. So we're saying that 335 is less than or equal to 90, which is impossible. Okay. So effectively, we know that d is not equal to 7, so d has to we know that d is not equal to 2, right, because that case led to a contradiction, so d has to equal 7 if there is a solution. Okay, so now let's consider the case where d is equal to 7. Then basically rearranging our equation gives us sort of this thing on the right-hand side here, that 10c minus 65b is equal to minus 495. And then you can basically divide both sides of that equation by 5 to get that 2c minus 13b is minus 99. And at this point, we can kind of divide both sides by 13 and equate the remainders that I get, because I'm saying that those two, I'm saying that these two sort of integers are the same thing. 2c minus 13b is the same as minus 99. So of course, when I divide both of those integers by 13, I get the same remainder because they're the same thing. So if I divide the left-hand side by 13, obviously 13b is going to give a remainder of 0, and 2c gives a remainder of 2c. So the remainder when I divide my left-hand side by 13 is 2c. The remainder when you divide minus 99 by 13 is 5, because minus 104 divided by 13 is minus 8. So minus 104 is divisible by 13, and then if you plus 5 to that, you get minus 99, which is my right-hand side. So this right-hand side here is 5 more than a multiple of 13, because minus 104 is a multiple of 13, so it leaves a remainder of 5 when divided by 13. Okay, cool. So we know that 2c has to be congruent to 5 modulo 13, or in other words, when I divide 2c by 13, I get a remainder of 5. And that's also just saying that the remainders that I get when I divide both of these sides by 13 are the same, right? So both the statements I just made are the same thing, basically. And obviously, we know that since c is going to be a digit, it has to be between 0 and 9. So 0 is going to be less than or equal to c is going to be less than or equal to 9. And effectively, the only solution that you actually end up getting once you just kind of plug in those values of c for that congruence is going to be 9, because effectively 2 times 9 is 18, which is 5 more than a multiple of 13. So this equation is only true when c is equal to 9. Any other values of c between 0 and 9, including 0, don't work, right? If c is 0, you don't have 0 is obviously not 5 more than a multiple of 13. It is a multiple of 13. So, you just try out those values of c, and the only solution you end up getting is c equals 9. So c has to equal 9, and then substituting c equals 9 into this equation here with 2c minus 13b equals minus 99 gives us that 18 minus 13b is equal to minus 99, which when you solve that gives you b equals 9. So the only actual solution then is going to be capital N equals 1997, which is quite fitting since this is a 1997 BMO1 paper. And obviously you can check that because the reverse of 1997 is 7991. You just read the integer from back to front. And of course that is 4 times 1997 plus 3. You can check that for yourself, but that is true. So yeah, now we can move on then, I guess, to problem 2, which basically gives us a sequence defined recursively by sort of these two sort of statements. The first term of our sequence is 1, and the nth term of our sequence is n plus 1 divided by n minus 1 times a1 plus a2 plus basically the sum of the first n minus 1 terms. So the nth term of our sequence is n plus 1 over n minus 1 times the sum of the n minus 1 terms that came before that term. And we're asked to determine the value of A1997, or what is the 1997th term in our sequence. So because we're working with this sort of recursively built sequence, and we have this sort of sum inside our nth term, right? Our nth term is defined in terms of the sum of the n minus 1 terms that came before it. So it's quite natural then to introduce this notation, which we call partial summation notation, which basically just defines this sort of new sequence with nth term s sub n to be the sum of the first n terms of our sequence that we're actually dealing with, right? So we basically define s sub n to be the sum of the first n terms of our sequence, a sub n, right, which is the one that they've given us in the question. But we're defining this as a new sequence, which is basically a sequence of partial sums. At least that's what we call it, right? So the nth term of that new sequence is going to be the sum of the first n terms of our sequence that we're actually talking about. Okay? And once we do this, then what you realize is that s sub n minus 1 is just the sum of the first n minus 1 terms in our sequence, which is exactly this thing here. So basically that means that our recurrence now becomes a lot cleaner, because it basically becomes a sub n equals n plus 1 divided by n minus 1 times s sub n minus 1. Okay? And of course, since this sort of nth term of our partial sum sequence, s sub n, is equal to s sub n minus 1 plus a sub n, right? Because s sub n minus 1 is just a1 plus a2 all the way up to plus an minus 1, and s sub n is the same but just plus an on the end here, then of course this is quite obviously true, right? Just by like using the definition of s sub n. Okay, so since we know this is true, we can hopefully turn this idea into a much cleaner recurrence for s sub n, and then work backwards to find our recurrence for to find our nth term for a sub n, which is basically the main idea here in this question. So now that we've sort of transformed our sequence a sub n into sort of this sequence here, which is n plus 1 divided by n minus, well, the nth term of our sequence a sub n is given by n plus 1 divided by n minus 1 times s sub n minus 1, and we know that s sub n is equal to s sub n minus 1 plus a sub n, then we can basically just replace a sub n with this thing here, which is n plus 1 divided by n minus 1 times s sub n minus 1. And that basically gives us this stuff on the right-hand side, right? Because we have s sub n minus 1 plus a sub n is s sub n minus 1 plus a sub n, which is this term here, right? And when you do the algebra, because you have s sub n minus 1 plus some multiple of s sub n minus 1, you can combine those two things into one term. And effectively what you end up getting is that this s sub n is equal to 2n divided by n minus 1 times s sub n minus 1. And so for any n greater than or equal to 2, because of course a sub n is only defined for n greater than or equal to 1, and we're working with s sub n minus 1 here, so if n is equal to 1, that's not even defined. So s sub n minus 1 is only defined for n minus 1 greater than or equal to 1, which means n is greater than or equal to 2. And so basically for values of n greater than or equal to 2, we get this recursive basically relationship for our sequence of partial sums, right? So the nth term of our sequence of partial sums is 2n divided by n minus 1 times s sub n minus 1. Okay? And basically, I know this notation here looks a bit daunting, but it's just what we call product notation. So basically, if I replace s sub n minus, because I know that this is true, right, for all n greater than or equal to 2, or natural n anyway, s sub n is equal to 2n divided by n minus 1 times s sub n minus 1. And so if I replace n with n minus 1, I get that s sub n minus 1 is 2 times n minus 1 divided by n minus 2 times s sub n minus 2. So effectively what I'm doing is I'm just replacing s sub n minus 1 with 2 times n minus 1 divided by n minus 2 times s sub n minus 2, and basically just repeating that until I get down to s sub 1, which I know will eventually happen because I'm just taking 1 away from n every single time, right? So eventually I'm going to get down to 1. I'm going to have a product of all of these terms here, which I've basically written here as a product from k equals 2 to n of 2k divided by k minus 1. Because we know that s sub 1 is basically our first term of our sequence, which we're given as 1. Because s sub 1 is the sum of the first term of our sequence given with term a sub n, right? Because we defined s sub n as the sum of the first n terms of our sequence a sub n. And so we know s sub 1 is going to be just a sub 1, and a sub 1 is 1. So we know s sub 1 is 1, right? And so effectively, once we get down to s sub 1, we can just replace that with 1. So ultimately, what we're working out here is just this product here. So s sub n is just given by this product from k equals 2 to n of 2k divided by k minus 1. Okay? And when you write out this product, basically this product here is just 2n divided by n minus 1 times 2 times n minus 1 divided by n minus 2 times 2 times n minus 2 divided by n minus 3, and so on and so forth. When you actually work out this product, what's going to happen is you're going to have these contribution of 2's here at the front, right? Because effectively each term is going to be 2 times n, or 2 times n minus 1, or 2 times k. And we're going to have n minus 1 terms because we're going from k equals 2 to n. So we're going to have a factor of 2 to the n minus 1, which we have to pull out the front of that product. And so then this product is basically 2 to the power of n minus 1 times the product from k equals 2 to n of k over k minus 1. And that obviously is going to basically telescope, because if you look at that product, there's going to be 2 divided by 1 times 3 divided by 2, and the 2's cancel on the numerator and denominator, and then times 4 divided by 3, and everything cancels. The only thing that doesn't cancel is the n at the very end. So we're left with 2 to the n minus 1 times n as our nth term of the sequence of partial sums. So we know that s sub n is n times 2 to the n minus 1. And using this relationship here that we started off with, s sub n equals s sub n minus 1 plus a sub n, we know that a sub n, therefore, is s sub n minus s sub n minus 1. And s sub n minus 1 is just n minus 1 times 2 to the n minus 1 minus 1, or n minus 1 times 2 to the n minus 2. So a sub n, therefore, has to be n times 2 to the n minus 1, minus, in brackets, n minus 1 times 2 to the n minus 2. Now, 2 to the n minus 1 is just 2 times 2 to the n minus 2, so we can factor a 2 out of that to get that a sub n is 2n times 2 to the n minus 2 minus n minus 1 times 2 to the n minus 2. We factor out 2 to the n minus 2. So that's just the same thing as 2 to the n minus 2 times 2n minus n plus 1, which is just the same as n plus 1 times 2 to the n minus 2. And that's the nth term for our sequence a sub n. At this point, we can easily find a sub 1997, which is the goal of the question, by just substituting in n equals 1997, which gives us 1998 times 2 to the power of 1995. You can obviously clean this up a bit more by dividing 1998 by 2 and getting 999. So you can basically write this as 999 times 2 to the power of 1996, so you get an extra factor of 2 from the 1998. But I don't think it's necessary. I mean, this is probably the answer. This you wouldn't lose marks for that, per se. Okay. So yeah, so the whole problem is basically saved by this sort of partial sum notation here. And the reason why that seems sort of obvious to include is because we have it literally built into the definition of our sequence. So if you ever see sequences like this, definitely try something like this in the future. It's a good idea. Okay, so now we're working with problem 3, which is a counting problem involving coins of value 1, 10, 100, and 1,000, and the currency is called pippins for some reason, I don't know why. But we want to basically find the number of ways that I can use those 4 coin valuations to pay exactly 1997 pippins. So obviously, just to get some intuition for this, I could use only the 1 pippin coin. 1997 of those 1 pippin coins gives me 1997 pippins, right? So that's one of the ways I can pay that amount. But I could also pay 1,000, and then let's say 9 hundreds, then 9 tens, and then 7 ones, and that's the same thing. So how many ways can I actually pay 1997 pippins with these 4 coin valuations, basically? Here's sort of a clean solution to that problem then. If we, first of all, define A, B, C, and D to be the numbers of 1, 10, 100, and 1,000 pippin coins used, then effectively what we want is A, right? So we want 1 times A, because A is basically has a value of 1 pippin. So if I have A 1 pippin coins, I'm going to have a value of A pippins. Plus 10B, because B is my number of 10 pippin coins. So if I have B 10 pippin coins, my valuation in pippins is 10 times B. Same for C and D. So we get that A plus 10B plus 100C plus 1,000D is equal to 1997, because we want to get 1997 pippins. Okay, so effectively, because there is a 1 pippin coin, right? So basically, because we have this sort of 1 pippin coin here, A, once I fix B, C, and D, A is kind of fixed, right? As in, once I choose what B, C, and D are, I can immediately find A, and it's guaranteed to be an integer because I can just subtract 10B at 100C at 1000D from 1997. So as soon as I choose B, C, and D, A is forced. So all that we really need to find are the number of triples B, C, D satisfying this equation, inequality, I should say here. 10B plus 100C plus 1000D needs to be less than or equal to 1997. Right? If it's less than 1997, then we're going to have some number of one pippin coins that we need to use to get to exactly 1997. If it's equal to 1997, then A is 0, right? Because then we don't need any 1 pippin coins. So this is the inequality now which we need to solve. Okay? Cool. All right. So ultimately, since we know that 2 times 1,000 is obviously 2,000, which is greater than 1997, D has to be 0 or 1. Because if D is equal to 2, then that left-hand side is going to be greater than 2,000, right? Because B and C are both non-negative integers. They could be 0 or some positive number, because the number of coins I'm using, right? So it has to be 0 or some other positive integer. Okay, So there are only two cases, d equals 0 or d equals 1, and we can split into cases here. First of all, let's think what happens when d is equal to 0. Well, if d is equal to 0, then using this inequality that we obtained up here, we just get that 10b plus 100c has to be less than or equal to 1997, because d is 0, so that term basically vanishes. And then we know that c, basically the value of c, can be anything from 0 up to 19, right? Because c can't be 20, because if c was 20, then the left-hand side would be greater than 2000. Again, the same logic that we use for saying d has to be 0 or 1 applies here. C has to be some integer between 0 and 19, right? Including 0 and 19. But it can't be 20 or anything greater than that, because if it were greater than that, the left-hand side would be greater than 2000, but we want it to be the left-hand side to be less than or equal to 1997. So basically, c has to be one of these integers from 0 to 19. And for each value of c, I can basically calculate using this inequality how many values of b I have in terms of c. That's basically what I'm doing here. So if I were to rearrange this inequality, I would get that 10b is less than or equal to 1997 minus 100c. And then I can divide both sides by 10 to get that b would have to be less than or equal to 1997 minus 100c divided by 10. However, that's not guaranteed to be an integer, so we have to take the floor of that value, right, to basically ascertain, which basically just means you round it down to the nearest integer to calculate which values of b I'm allowed to have for a given value of c, okay? That's such that this inequality is satisfied, right? And obviously then, once we've chosen that, the value of a is going to basically account for anything else which we've missed, right? Because b, as in all we care about is finding values of b and c such that this inequality is true. And then once we have b, c, and d, we can figure out a because we can just subtract 10b plus 100c plus 1000d from 1997. So for each value of c between 0 and 19, we can basically have b taking any value from 0 up to the floor of 1997 minus 100c divided by 10, which, is basically just going to be 199 minus 10c. And you can kind of reason through that sort of logically. If c is 0, then you get 199.7. The floor of that as you round that down to 199, right? And so the largest value of b when c is equal to 0 is 199, which makes sense because if it was 200, then you get 2000 on the left-hand side, which is not less than or equal to 1997. So that makes sense, right? And so the only reason that we're taking the floor here is because we want b to be an integer. And so if you just sort of work with different values of c, you'll see that basically the sort of this quantity here, whenever you round down 1997 minus 100c divided by 10, you always get 199 minus 10c. Because basically you can split this sort of fraction up into 199.7 minus 10c, right? The floor of that. The 10c is going to be doing nothing. The 0.7 is doing all the sort of work in terms of that's the bit that you're going to get rid of when you round it down. So you can basically say 199.7 minus 100 minus 10c rounded down. It's always going to be 199 minus 10c because the 0.7 is always going to we're always going to be getting rid of that when we round it down. So basically, just to reiterate, for any value of c between 0 and 19, b can take any value from 0 all the way up to this floor, which is just 199 minus 10c. So there is going to be 200 minus 10c possibilities for b for every single value of c, right? So basically, we've found how many possibilities there are for b in terms of c once we fix a value of c between 0 and 19. And so we basically just sum those possibilities where from c equals 0 to 19 to get the total number of possibilities in this case where d is equal to 0, right? Because this is basically a function of c, right? So the number of possibilities that b can take is depending on what c is, obviously, right? Because that's going to change what the value on the left-hand side is. So that's going to force my b to have to be smaller and smaller and smaller, intuitively, right? So for each value of c, the number of sort of options I have for b is going to be 200 minus 10c because you also have 0 as well, so you have to add on 1 to 199 minus 10c. And then effectively, to actually calculate the total number of possibilities there are for values of b and c which solve this inequality, which is the same as the total number of possibilities for a, b, c, and d in the case where d is equal to 0, we can just basically take different values of c and add together 200 minus 10c for each of those different possible values of c, which is the same as doing this sum here. The sum from c equals 0 to 200 minus 10c, the sum from c equals 0 to 19 of 200 minus 10c is just going to give us the total number of possibilities. And when you actually evaluate that sum, you get 2100. Okay, I'm assuming you know the typical methods to evaluate sums like these. Hopefully you should know by now that the sum of a constant from the sum of 200 from c equals 0 to 19 is just going to be 20 times 200, right? And then the sum from c equals 0 to 19 of c is going to be your typical n times n plus 1 divided by 2. So that's going to give you 190. Okay, so basically what you're doing there is you're doing 20 times 200 minus 10 times 190, which gives you 2100, exactly as the set, right? So that's the case when d equals 0. That's how many possibilities there are if d is equal to 0, for which this equation here is true. What about if d equals 1? Oops, sorry. What about if d equals 1? Well, if d equals 1, then we basically get this plus 1000 term here, so we subtract that from both sides. To get that 10b plus 100c has to be less than or equal to 997. And again, using a very similar idea, for each c, in this case, c can only be between 0 and 9, not 19, because if it was 10, the left-hand side would be greater than 1000. Greater than or equal to, I guess. But effectively, we know that c has to be between 0 or 9. Between 0 and 9, it has to be an integer, so it has to be one of these possibilities. And for each value of c in this case, b can take the values from 0 all the way up to this floor here, which you just get by rearranging this inequality, which is the same as 99 minus 10c in this case, because 99.7 gets rounded down to 99 every time. And so the total number of possible values of b in this case, for each value of c, is 100 minus 10c. And so, it's actually been cut off here. I didn't mean to cut that off. But basically, you basically just find the sum, similarly to how you did here. You find the sum from c equals 0 all the way up to 9 of 100 minus 10c, because you have values of b. You have 100 minus 10c possibilities of b for each value of c, because b could be 0, 1, all the way up to 99 minus 10c. So that gives you 100 minus 10c possible different values of b for each value of c. And then you just sum those values from c equals 0 to 9. So you do the sum from c equals 0 to 9 of 100 minus 10c. And when you do that, you get an answer of 550. And basically adding those two possibilities together, right, because d has to be 0 or 1, you've dealt with both those cases. Once you add those two possibilities together, you get 2100, which is from here, plus 550, which is from this case here, equals 2650. So 2650 different ways of getting 1997 using those 4 coin valuations. And that is the that's the question. Okay. It's quite a good example here of what we call organized casework, right? So you have to be quite organized in the way that you go about doing this. And the nicest possible way that you can go about organizing that casework is by talking about the values of d. Okay? And first of all, you also have to realize that a is kind of useless. It's determined by everything else. Once you realize that, you should hopefully realize that d is the easiest thing to work with in terms of cases. Because there's like lots of different possible values for c that I could have. And so I would have to do a lot more work in terms of doing casework with c than I would with d. So it's kind of just, you got to be very careful and organized about the way you go about this casework. But yeah, I mean, other than that, pretty nice question. Okay, here we go. So now we have problem 4. So now we're coming to the geometry problem, which is where things start to get a little bit interesting. But do stay with me though, even if you don't like geometry. I think this problem is quite a nice problem. So we have a convex quadrilateral ABCD. So again, all that really means is that I have a quadrilateral where each of the angles inside it is less than 180 degrees. Okay, so we have a convex quadrilateral ABCD, and PQ, R, and S are the midpoints of AB, BC, CD, and DA respectively. And we're told that the midpoint of the quadrilateral PQRS is we're told that the midpoint quadrilateral, PQRS, so the quadrilateral formed by basically those midpoint chords, has area 1. And we have to prove that the area of ABCD is equal to 2. So just to give this a bit of perspective, I guess, as you can see here, this is kind of what our diagram looks like for this sort of geometry problems. Usually it's a good idea to draw diagrams representing, whatever they're asking you to basically work with. And in this case, as you can see, we have our convex quadrilateral ABCD. Okay, and basically all of the angles inside that quadrilateral ABCD are less than 180. Then I have my midpoints of each of my sides. So P is the midpoint of my side AB, Q is the midpoint of my side BC, R is the midpoint of my side CD, and S is the midpoint of my side AB. Okay? And we basically need to we're told that the area of this inside quadrilateral PQRS is 1. And we basically need to prove that the area of ABCD therefore has to equal 2. Because we know that what we're saying is that if this area here is 1, the entire area has to be 2. That's what we're trying to prove. Okay? So we can start by basically using these square brackets here to start talking about area. And if you have a look at the diagram, then you'll see that the sort of construction that we sort of are told to sort of invoke on our quadrilateral in terms of the midpoints gives us these 4 triangles here, right? So it splits ABCD into an inner quadrilateral PQRS, which we've shaded here, and 4 triangles. Triangle ASP, which is going to be this triangle down here. Triangle BPQ, which is going to be this triangle here. Triangle CQR, which is this triangle over here. And triangle DRS, which is this triangle over here. So we have 4 triangles as well as our inner quadrilateral that are formed when we do that sort of construction, which they asked us to do in the question. So therefore, the area of the entire shape, or the entire quadrilateral ABCD, is the area of PQRS plus the areas of each of the individual triangles. That's what this statement here is saying. And so now what we need to do is figure out the areas of those triangles, basically, or somehow relate those areas somehow relate the areas of those triangles to the area of the entire quadrilateral somehow. And yeah, so you can see here, this is basically what I just said. We have our entire quadrilateral ABCD, split it up into our sort of midpoint quadrilateral PQRS and our 4 triangles. And what I'm saying is that the area of the entire thing is just the sum of all those shaded areas there. And this is a diagram which will become more apparent when we look a bit more at this question in a second. So I'll come back to that. But okay, because we know that P and S are the midpoints of AB and AD. So if we go up here, P is here, and that's the midpoint of AB. S is the midpoint of AD. Okay, so therefore we know that AP is a half of AB by definition, because P is the midpoint, and AS is a half of AD. Okay, and of course the angle at A, well, we don't know what it is, but it could be anything as long as it's less than 180 because we have a convex quadrilateral. So in degrees, that angle could be anything less than 180 degrees. However, it's the same for 2 different triangles that we're trying to consider here. So if I consider triangle ABD, right? So if I consider that triangle ABD, which I haven't really drawn in here, but just imagine that there was a line going from B to D, and you look at that triangle ABD, and you look at triangle APS, they both have the same angle at A. Okay? Just because basically they're using the same point there. So the angle isn't changing, and you can kind of see that for yourself. If you sort of just draw in a line from B to D, you look at triangle ABD, that's the same angle at A as triangle APS. Okay? And so as a result, since we know the area of a triangle is a half AB sine C, then we know the area of ABD, triangle ABD, is going to be a half AB times AD times this angle here at A. And then we know the area of triangle APS is going to be a half AB times a half AD times sine of this angle here, which is the same. So by equating those 2 areas, we'll see that basically the area of this triangle ASP here is actually going to be a quarter exactly of the area of triangle ABD here, because AS is a half AD and AP is a half AB, which is basically what I'm saying here. So we know the area of triangle ASP is a quarter of the area of triangle ABD. And what I've done in this example here with a dotted line is show you that exact or try and illustrate that exactly with triangle BPQ and BAC. Okay, and you're using the same thing basically because you know these are midpoints. So the area of BQP is a half BC times a half BA, because BP is a half BA and BQ is a half BC, times sine of this angle here. And the area of ABC is just going to be a half AB times BC times sine of this angle in here, right? So if you just look at both those areas, you'll see both of those sort of formulae for the areas of those 2 individual triangles. You see that the area of triangle BPQ is a quarter of the area of triangle ABC. And you can repeat this for each of the 4 shaded triangles in the diagram to get these relationships here. So triangle BPQ, the area of that triangle is a quarter of the area of triangle ABC. And then sort of these other relationships here are true as well. And you can just have a look at the diagram there. Pause the video if you want to see that for yourself. But ultimately, if you understood the first 2 examples, the other 2 are exactly the same. And so therefore, if we add up the areas of each of our triangles then, so this is basically, this quantity here is the sum of the areas of our 4 sort of shaded triangular regions here. And we substitute in the expressions for each of those in terms of ABD, ABC, BCD, and CDA. We get that the sum of the areas of our 4 triangles is a quarter times the sum of each of these individual larger triangle areas, right? So we have the area of triangle ABD, area of triangle ABC, area of triangle BCD, and the area of triangle CDA. Well, the area of triangle ABD plus the area of triangle BCD is going to be equal to basically the entire area of the quadrilateral, right? Because in that case, we're just splitting the quadrilateral along the line BD and splitting it into 2 triangles and saying that the area of those 2 triangles is of the entire area. So the area of triangle ABD plus the area of triangle BCD is just equal to the area of the entire quadrilateral ABCD, right? So ABD plus BCD is equal to the area of the entire thing, right? So those 2 areas and together give you the area of the entire thing. And equivalently, the area of triangle ABC plus the area of triangle ACD gives you the area of the entire quadrilateral, right? Which is what I've said over here. And so therefore, we can clean up this expression even further to say that the sum of the areas of our 4 smaller triangles is a quarter times the sum of these areas, which is equal to a quarter times the sum of the area of the entire quadrilateral with the area of the entire quadrilateral. So you get that this entire sum here is a quarter times 2 times the area of the entire quadrilateral, to get that the sum of these 4 triangular regions is equal to 1/2 times the area of the entire quadrilateral, quite nicely. So basically, the sum of these 4 triangular regions is 1/2 of the entire area of the quadrilateral. And so from the first part of the proof, we had this sort of fact, right, by splitting up the triangle into the sort of midpoint quadrilateral and the 4 other triangles. And now we know that the sum of the areas of those 4 other triangles is 1/2 times the total area of the quadrilateral. So we substitute that in, bring everything onto one side. The area of the midpoint quadrilateral is 1/2 times the area of the entire quadrilateral. And so therefore, because we know that the area of PQRS is 1, we can substitute that in to get that the area of ABCD has to be 2, exactly as required. So so the midpoint quadrilateral in this case has exactly half of the area of the outer convex quadrilateral, and since the inner area is 1, the outer area has to be 2. Okay, and here you go. You can kind of see that entire result here, which is being summarized by saying that the area of this midpoint quadrilateral here is exactly 1/2 of the area of the entire quadrilateral. And I even have quite a nice, if I can get it up, quite a nice sort of Manin demonstration of this thing, basically telling you that no matter what your convex quadrilateral is, as long as it's convex and the angles inside are less than 180, then you're guaranteed to have this property for your midpoint quadrilateral no matter what it is. So let's have a look at this. So we have our quadrilateral, and then we're going to form our midpoint quadrilateral like so, and we have our area of our 4 triangles. And this ratio always turns out to be true, right? So the area of the midpoint quadrilateral is always half the area of the total quadrilateral. As you can see, we're changing the shape of that quadrilateral, but the ratio isn't changing. And that's what we basically just proven, which is quite neat. Okay. So now if I can go back then to the PowerPoint, a couple seconds. Trying to see which one I need to go to. No, it's not that. It's that. There we go. Okay. Final problem now. Here we go. So, to finish, we have problem 5 asking about the reciprocals of 3 positive real numbers, x, y, and z. There are 2 parts to this question. The first part asks us, if we know that x plus y plus z is greater than or equal to 3, is it necessarily true that 1 over x plus 1 over y plus 1 over z is less than or equal to 3? And the second part of the question asks us, if we know that x plus y plus z is less than or equal to 3, is it necessarily true that 1 over x plus 1 over y plus 1 over z is greater than or equal to 3? Okay, so basically the same kind of question, but we're flipping the sign of the inequality here from a greater than or equal to a less than or equal to from the second part of the question, and also the sign of the inequality here from a less than or equal to the greater than to a greater than or equal to sign down here. Okay, and as I've written here, they do look like sort of mirror images of each other. So you might think, okay, surely they're either both true or both false, but actually it turns out that the first one is false, but the second one is true. So even though you flipped these inequalities exactly, both of them from the first part to the second part, that doesn't necessarily mean that you're going to keep the that doesn't imply that if this statement is true, then this statement is true, and vice versa, right? So these 2 statements are actually not both true at the same time. Okay, so the first one is false and the second one is true. Perhaps rather surprisingly, but how do we actually go about showing that? Well, it's quite easy to show that the first one is false, right? So in order to disprove like a statement for all for all values of x, y, and z, right? Because we know that x, y, and z are positive real numbers. What we have here is a universal statement. So we're saying that for any choice of x, y, and z, as long as this is true, they sum to something greater than or equal to 3, this statement is true, right? So that's like a conjecture. In order to disprove that, we can just find a counterexample, right? So the counterexample which I've come up with here is taking x to be 1/2, that's a positive real number, y to be 1, and z to be 3 over 2. Then we know that x plus y plus z is 1/2 plus 1 plus 3 over 2, which is exactly 3, so that is greater than or equal to 3, namely it's equal to 3. Right, so we have our hypothesis being satisfied. However, when we do 1 over x plus 1 over y plus 1 over z, you get 2 plus 1 plus 2 over 3, which gives you 11 over 3, which is clearly greater than 3 because 11 is greater than 9. Okay, so the conclusion is just completely false. Okay, and so therefore we definitely do not have that 1 over x plus 1 over y plus 1 over z is less than or equal to 3, when x plus y plus z is greater than or equal to 3. And that's that. That's all you really need to do. Now, for the second part of the inequality, we need to use a very, very... in order to prove this is true, actually, because the second part is true, to prove that it's true, I'm going to now prove something called the Cauchy-Schwarz inequality, which basically tells you this statement up here. So I'm going to prove it for the 3-variable case, where we have basically 3 things being summed in each of these 2 brackets here, right? So if it was a 4-variable case, we'd have A, B, C, and D, then P, Q, R, S in the second bracket or something like that. But we only need the 3-variable case for this question, so that's what I'm going to prove. And I decided to write out the proof here for people that might not have ever seen it before, because I think it's something that is used quite a lot actually at Olympiad level, so quite good to have a proof. So basically all the Cauchy-Schwarz inequality tells you is this fact here, that for any basically real numbers a, b, c, p, q, and r, we're always going to have that a squared plus b squared plus c squared times p squared plus q squared plus r squared is greater than or equal to ap plus bq plus cr all squared. Okay, now this is going to be really, really useful for our question, and it will become apparent why later. But for now, just appreciate what we're trying to prove, basically, right? This is the statement we're trying to prove. Okay, and really, all you kind of need to do, well, if you wanted to actually sort of like work through this sort of scratch work to come up with a proof here, you'd be doing the reverse of what I'm about to show you. What I'm about to show you is going from the endpoint here, because you might be thinking, how the hell do you even get this thing here? Now, in order to get that, you have to start with the thing you're trying to prove and work backwards, and then when you actually prove it, you work forwards again. But I'm going to go with the forwards proof anyway. So first things first, we know that a sum of squares of real numbers is always non-negative, right? So if I have these three quantities all squared and I add them together, of course I'm going to get something greater than or equal to 0, because I can't get anything less than 0, because none of these terms are ever less than 0, because the squares are real numbers. So aq minus bp all squared plus ar minus cp all squared plus br minus cq all squared has to be greater than or equal to 0. And then all we need to do is just expand this, so you can just expand it step by step, and you're going to get a squared q squared minus 2abpq plus b squared p squared plus a squared r squared minus 2acpr plus c squared p squared plus b squared r squared minus 2bcrq plus c squared q squared has to be greater than or equal to 0, because we know this thing is greater than or equal to 0, so we're just expanding that and it's still greater than or equal to 0. Now we can rearrange terms, so we group together these a squared terms to get that a squared times q squared plus r squared plus b squared times p squared plus q squared plus c squared times p squared plus q squared minus 2abpq minus 2acpr minus 2bcrq has to be greater than or equal to 0. And at this point, you can basically realize that this thing here that we have on the left-hand side is exactly the same as this quantity here. Okay? A squared plus b squared plus c squared times p squared plus q squared plus r squared minus ap plus bq plus cr all squared. Okay? As I said, that might not be necessarily obvious to you because we're working in the forwards direction, but whenever you work in the backwards direction for this proof, you would be starting out with the thing you're trying to prove, moving everything onto one side, expanding it. Then you'd get a form like this, which you would rearrange into a form like this, and then try and write that as a sum of squares, which is a bit easier to do, I guess. Although, to be fair, even finding that as a sum of squares is actually quite difficult. This proof is not very intuitive, to be honest with you. You do have to sit there for a bit if you wanted to actually prove this. But, just appreciate it for now. Because this is true, right? So if we basically rearrange all the terms that we had up here, we get this, which is obviously going to also be greater than or equal to 0, so the sum of squares is greater than or equal to 0. And this thing here turns out to be exactly the same as this thing. So that exactly gives us that a squared plus b squared plus c squared times p squared plus q squared plus r squared minus the sum of all that stuff squared is greater than or equal to 0. And then, of course, moving the sort of this term onto the right-hand side here gives us the required result. That a squared plus b squared plus c squared times p squared plus q squared plus r squared is greater than or equal to ap plus bq plus cr all squared. So that's your Cauchy-Schwarz inequality, which we're going to be able to use in this question. So in this case, we're going to apply the inequality with a being equal to root x, so that a squared is equal to x, b is going to be equal to root y, so that b squared is equal to y, and c is going to be equal to root z, so that c squared is equal to z. Similarly, we're going to have p being equal to 1 over the square root of x, so that p squared is 1 over x, q is 1 over the square root of y, so that q squared is 1 over y, and r is 1 over the square root of z, so that r squared is 1 over z. So therefore, we're going to have that a squared plus b squared plus c squared is equal to x plus y plus z, and p squared plus q squared plus r squared is equal to 1 over x plus 1 over y plus 1 over z. And also we're given that AP is obviously root x times 1 over root x, which is 1. BQ is just root y times 1 over root y, which is also 1. And CR is root z times 1 over root z, which is also 1. So AP plus BQ plus CR is 1 plus 1 plus 1, which is 3. And so this right-hand side is going to be 3 squared. So if we just basically plug all of that stuff in terms of x, y, and z, and this 3 here into our Cauchy-Schwarz inequality, we get the following, that x plus y plus z times 1 over x plus 1 over y plus 1 over z is always going to be greater than or equal to 9 for real numbers x, y, and z. So at this point, since we have this inequality here, we can just rearrange that by dividing everything through by x plus y plus z to get that 1 over x plus 1 over y plus 1 over z is going to be greater than or equal to 9 divided by x plus y plus z. And in the question, we are told that x plus y plus z is going to be less than or equal to 3. So because we know that x plus y plus z is less than or equal to 3, we can just rearrange that to get that, if you basically multiply both sides by 3 of this equation here, you get that 3 times x squared plus y, 3 times x plus y plus z is less than or equal to 9. And then dividing both sides by x plus y plus z gives you that 9 divided by x plus y plus z is greater than or equal to 3. So 1 over x plus 1 over y plus 1 over z is greater than or equal to 9 divided by x plus y plus z, which is greater than or equal to 3. So therefore 1 over x plus 1 over y plus 1 over z is greater than or equal to 3, which is exactly the statement that we were trying to prove, right? That they asked us to prove in part II. Okay, so, and obviously also the sort of, this is equal to 3 when x is equal to y is equal to z is equal to 1. Okay,